DataOps is an engine. It can be used to implement any data warehouse architecture. The project I showed earlier is a sort of a standard Kimball model. We have a demo project that implements the data vault, data warehousing architecture. So there is no data warehouse architecture imposed by the DataOps platform or the MDA model for that matter. But we do have a lot of experience on what works in 95% of cases. Effectively, if you think about the sort of standard Snowflake, and most data warehouses follow the same thing, the standard hierarchy, you have a concept of tenant. So this would be your account. Within that, you've got databases. Within that, you've got schemas. The DataOps platform is very strongly opinionated on the structure here. And when you think about it, when we showed that example earlier, when we did a feature branch and we said, oh, we'll clone the production database and create a feature branch version, for that to work, there has to be a very standardized, structured way that we use the concept of databases and schemas. So the way we use tenants, the way we use database, the way we use schemas is very strongly opinionated. There is a bit of flexibility in there, but there has to be a good reason to diverge from our standard model because everything is set up for that standard model. What you do here at the table and view and materialized view levels, that's completely up to you. We are partially opinionated, like we say, don't create a view that joins 53 other things together, split that down into smaller models, as we talked about extensively earlier, have complex systems emerge from smaller building blocks, but there's a lot more flexibility there. That's a lot more that has to adapt to your business, whereas the structure of the top three is really much more something the DataOps platform uses to achieve all of the automation and stuff that we've already seen. So it's an example here of sort of how this manifests in practice. We assume a prefix of DataOps. You might choose to, a particular project or program name or something, but then effectively we have standard databases. So like you might get DataOps production, DataOps QA, and then you end up with DataOps feature branch databases, which we saw being created earlier. Each of these have their own warehouses in Snowflake for ingestion and transformation. Why is that? Remember, the principle of a feature branch is isolation. There's nothing I should be able to do in my feature branch which affects other people. So that's great. We've feature branched our code. We've got isolation there. We feature branch our data. We've got isolation there. But if we're sharing the same warehouse, compute concept in Snowflake, and as part of our work in our feature branch, we accidentally write some enormously erroneous query that there's a whole bunch of self-joins and this, that, and the other, and it chews up CPU resources for 2 hours. If we're sharing the same warehouse as production, whilst all of our data is separated, we've just slowed down or ground to a halt the production workloads, which is unacceptable. That violates our principles of separation. We have production and QA use their own dedicated warehouses. We can have dedicated warehouses for every feature branch, but it's a little bit of a pain to manage. So generally we say, let's have one development ingestion warehouse and one development transformation warehouse, and we share that across all the feature branches. So you end up in this model with a total of 6 warehouses. Ingest and transformation for production, ingest and transformation for QA, and then a shared one, ingest and transformation across all feature branches. And you can see the default population model here. Production is how you expect it. It's actually ingesting from sources. QA does the same because you have to have something that emulates production perfectly that is before production. So you have to do the raw ingestion twice, but everything below that, all the feature branches are, their default population is cloning, and then any incremental work they add on top of that. So if we think back to this diagram that I had earlier, the sources on the left-hand side, the structure here doesn't require much thought. The structure here is basically defined by the ELT process. The structure here will represent very close to one-for-one the source systems themselves. The structure on the right-hand side is defined by your business. This is what your users want to see. It may have come out of a database modeling tool, or it may have come out of just iterative work with the user, but the right-hand side is defined by what your business needs. So those two are relatively inflexible. They're relatively decided or prescribed for you. Where you do have flexibility and where you do have a lot of decisions to make, which can be right or wrong, is the stuff in between. And this is where most of our opinions and recommendations and best practices come and say, okay, your sources are defined for you. They are inherent. Your outputs for the business are pretty much restricted and defined by what the business needs. But how you translate between one and the other, that's where we strongly advise that you do things in certain ways, a lot of which we talked about before. Just briefly, so materialization strategy. So we've talked about each of these. I've used the term model lots of times, and you've seen what a model is. A model is a set of a bit of SQL and some templating. You can materialize those, i.e. have those manifest in the data warehouse in one of a bunch of different ways. The 4 most common ones are tables, as you would expect, views, as you would expect, ephemeral. Essentially what ephemeral means is it exists in the system as a logical entity, but it never gets materialized inside Snowflake. So if you imagine, for example, the curation country region, the model at the top, if that was ephemeral, when the system was building the calculation dimension shipping address table, it needs to reference that, but it wouldn't do a subquery on a table. It would simply compile up the query for country region and include it effectively as a subquery or a CTE. So it just, the system will work out what it needs to compile up and get its data. And it is sometimes that's pretty useful. If you've got very large systems, you can have hundreds and hundreds of these models, and actually a lot of them you don't need to see at an intermediate stage. You want to define them, and you want other systems to use them, get all the benefits of inheritance, but you don't want to actually see them as objects inside Snowflake. The final materialization here is incremental. Imagine that one of these tables has got 100 billion rows in. Entirely possible. You don't necessarily want to, and imagine you've got 4 models hanging off the right-hand side. You don't necessarily want to take all billions of rows every single time you regenerate it. So the incremental model, effectively, it's the same at the modeling transformation layer as incremental ingestion would be. It says there's some new data been added from the ingestion process, but rather than rebuilding all 100 billion rows, let me just rebuild all the rows I need to build to make my model valid. And they use the terms very reservedly there because you can't just say, give me all the new rows. Imagine that I've got a model that says, give me the average number of sales per day. And let's imagine that I've got data coming in every hour. If at 4 o'clock in the afternoon, I can't just say, give me the data from 3 to 4 and update. My aggregate now needs to rerun all the data from midnight, which is fine. And that's only a couple 100,000 rows. That's simple and trivial. I don't mind rerunning today's data. What I don't want to do is rerun the last 10 years worth of data. So there's a lot of sophistication around exactly how you set these incremental models up such that you can do complex aggregations and have them be valid and regenerated, including going back in time a little bit, but without having to regenerate everything. So I won't go through the pros and cons of each of these. Most of them, as you expect. Tables are generally higher performance, that you get visibility of them for debugging purposes, but you're paying a little bit more storage costs. Generally, as a very, very simple rule of thumb, if you create all of your calculation and curation models as views and all of your consumption models as tables, you get a pretty good compromise of speed and performance and storage and cost. All the consumption models, which are things that the users are going to be hitting, are materialized as tables. So they're very, very fast. All the caching works beautifully. All of the objects to the left-hand side of that are reviews, so you can go and run automated tests against them. You can see them if you're doing debugging, but they're not actually using any storage because they only actually do anything when they're being queried. So that's a pretty good hybrid model to start with. So just to give you an idea of what an incremental model looks like, again, it's very straightforward. It's very templated. You just put an is incremental wrapper around a where clause. So the simplest one here would be to say, let me just grab everything where the timestamp in the table that I'm reading from is greater than the max timestamp in my table. So it just says, give me all of the rows that I haven't seen a timestamp for. Very, very simple, very, very straightforward. That's what it looks like if you want to do what I described before, which was a kind of a rolling daily update. You basically just truncate it back to a day and you say, give me everything that is for today. And it will just keep regenerating that for the day's worth of data, and all of the calculations will be correct without us worrying about, was it row added this hour or last hour? It doesn't matter. We just give me all the data for today and I'll recalculate those aggregates. So if we go back to these kind of 12 rules based on what we've talked about earlier and this afternoon, I think we can pull these out to sort of 5 or 6 key characteristics. If we look at the model definitions, the way we create models, they're small, they're maintainable, they're understandable, they're testable, they're composable because we can assemble these things, they're debuggable because unless we've got them specified as ephemeral, you can actually see each of the stages. That's a really important part. If you think to when we're going to be doing this stored procedure work and we're going to break one massive thing down into 20 or 30 smaller components, we're going to want to be able to see in real time the outputs of each of those components, certainly while we're doing all of the work. Now, it might be that once this has been in production for 3 months, everyone's completely happy with it. Then we just say we'll change the materialization to be ephemeral because we don't need to see the objects in the data warehouse each time. But certainly anytime you've got any question where you want to do debugging, the first thing you do is make sure they're at least views so you can see physically the output of each of these models at each stage. A quick note on constraints and tests. Generally, operational databases make use of constraints. Constraints prevent things from happening. Must not be null. If you try and insert null, it will fail. Must be unique. If you try and insert a data value that's already there, it will fail. For referential key integrity, if you try and insert data that doesn't exist in the foreign key table, it will fail. Data warehouses generally don't use constraints. Interestingly, a lot of data warehouses allow you to specify constraints, but they're not enforced. They're there as sort of rules and advisories rather than enforcement. Why is that? Simple: performance. Having those constraints makes data transactional systems slow. Snowflake can ingest and process billions of rows a second. Very few operational databases can. Why? A lot of good reasons, but one of them is it doesn't enforce constraints. And actually, there's a lot of good reasons why you wouldn't do that. In a transactional database, referential key integrity is probably critical. But given that our data warehouse has got a lot of history in it, it may be that we've got history of things that no longer exist in the operational database anymore. So it might be in the data warehouse, it's entirely valid to not have referential integrity because we've got a superset of data and we shouldn't be enforcing that. The way that we view this is that there are certain things that you want to do. Referential integrity is a good example, but we never try to break the data warehouse model of imposing these constraints. What we do is write tests for them. And if you remember when I talked about the different pipelines, I said one of the pipelines you could do would be a weekly deep data test. So you might say, okay, I've got 2 billion row tables here. They should have referential integrity between them. I certainly don't care about checking that every hour. I probably don't care about checking that every day. But once a week, it would be nice to run a referential integrity check and just give me a report of any rows which fail that test. And then I can go in and say, is it valid? Is it a problem in the source system? Is it something I need to clean up somewhere? So you test for them and you inform based on deviations, but you don't try and stop the day-to-day operation of the data warehouse because of it.